Okay, so this week we had an example FRQ and two that I asked you guys to try. Just for the sake of time, which one do you guys prefer to start with? I'll try to get through both, but just in case we can't, do you want to do this one from 2002 or this one from 2003? If there's no preference, I'll just go ahead and start in order, I guess. Okay. So starting with this one from 2002, I've got number of gallons PT of a pollutant changing at the rate of P prime T, where P is measured in gallons, or P prime rather, is measured in gallons per day and T is measured in days. There are 50 gallons of pollutant in the lake at T equals 0. The lake is considered safe when it contains 40 gallons or less of a pollutant. First thing they want to know is whether the amount of pollutant is increasing at T equals 9 and why or why not. Starting with Jade, what do we have to do first?
Can you repeat, please?
Yes, so we've got some number of gallons PT, and we were given P prime of T, that's in gallons per day, as a function here. And we know that there are 50 gallons already at time T equals 0. I want to know whether the amount of pollutant is increasing at T equals 9 and why or why not. What do we need to do?
Plug in 9 in the P prime T.
Perfect. So I'm going to plug 9 into P prime T. How will we know whether it's increasing or decreasing?
If value is negative, then it's decreasing.
Perfect. This is already a derivative. So if the value is negative, it's decreasing. If it's positive, or increasing. So let's go ahead and do that. P prime at 9 is equal to, and that would be 1 minus 3 e to the negative 0.2 times 3. I'm going to write 2 over 10 and then multiply by 3. Okay. So taking a look at this, is our answer going to be positive or negative? Over to Sai.
Negative.
Okay, this will end up being negative. See, this is question 2. So this would be with a calculator actually on the AP exam. If we weren't sure, we can estimate E as somewhere around 2.8-ish. It's like 2.81. P prime at 9 is going to be less than 0. Because P prime at 9 is less than 0, we could say that the amount should be decreasing. Element B.
Mr. Brandon?
Yes.
I heard that Imbi cannot using microphone now, so she will use chat.
Okay. Let me go ahead and pull up the chat then. Okay. All right, so in to catch you up to speed, we were on question 2 from the homework. There is some function p of t. We were not given the function though. We do have a function of p prime t, the derivative, measured in gallons per day. We are also told that at the beginning, sets t equals 0, there are already 50 gallons of pollutant in the lake, and that the lake will be considered safe when it contains 40 gallons or less of a pollutant. For part A, we wanted to know whether the amount of pollutant was increasing or decreasing at t equals 9, and why or why not. So Jade had us plug in 9 into p prime t in order to figure out whether it's increasing or decreasing. So this is already the derivative. We ended up getting a negative answer when we plugged in 9. So therefore, the gallons of pollutant was decreasing by day 9. Okay, for part B, I want to know for what value of t will the number of gallons of pollutant be at its minimum value, and then justify your answer. I'm going to look to in B. If I want to figure out what time the pollutant will be at a minimum value, what do I need to do? Integrate. So if I integrate, we'll get the total amount of pollutant. But in order to figure out whether the amount of pollutant is at a minimum, we'll actually need to work with a derivative. I'm going to jump to Jade would be next. Jade, what do we need to do with the derivative in order to figure out when the amount of gallons of pollutant is at a minimum value?
So p prime t is equal to 0.
Okay, so we can find the critical points first. In order to have a minimum or a maximum of a function, that relative minimum or maximum would need to have a slope of 0 at that point. If we're looking for an absolute minimum, then I would be looking at the start point and end point as well, potentially. Since our start point and end point, even though the slope is not 0, could be higher or lower than the points where our slope was equal to 0. But if we change direction, so have a relative maximum or a relative minimum, we'll have to have a slope of 0. So for part B, we can find a critical point, and then check to see if that's the minimum value. So Jade, you're right. I'm going to set this p prime of t equal to 0 first. So copying from a previous line. Okay. So I'm looking to set this equal to 0. What can I do from here if I want to solve for t? Who's next? Actually, that was just Jade. So Sai, you're up next. What's my next step if I want to solve for t?
Multiply ln to both sides.
I'm going to take natural log of both sides. Before I do that, though, I'm going to need to divide both sides by 3, I believe.
Okay.
So I'm going to do both of that really quick. This is 1 over 3 is equal to, right now I've got e to a negative power though. And I might actually be able to make this simpler if I throw this on the bottom of a fraction too. Two t over 10. Okay, so now I can cross multiply and then we can do your natural log. Okay, so after doing the natural log, Sai, what will we be left with for our next line?
Um,
I'm missing a T, aren't I?
2t over 10 equals to
Waste a lot more than I thought I did. Okay. Okay, sorry, go ahead.
2t over 10 equals to ln 3.
Looks good. And last step, solve for T.
Multiply both sides by 10 over 2.
Looks good. Okay, so I've got 5 ln 3. Double check really quick. We added this over to the other side, divided by 3, cross multiplied, took natural log of both sides. Over 10. Okay, multiplied by 10, divided by 2 should be fine. Oh, wait a second. It's the square root of T, not just T. Sorry, back at the original problem. I copied from this line, but this is actually, we plugged in 9 and got 3 here. This is the square root, I think. Yeah. That's okay. I'll go back and fix that really quick. So that means the only thing that's going to change is right now I've got a square root T, so nothing changes so far. I just need to go back and change our lines here. Okay. Missing too much, someone's going to be right. Root T equals 0. Okay, so I got one more step, sorry. Sorry, last step. Root T is 5 ln 3.
T equals to 5 ln 3 to the square.
Perfect. Okay, so this is our only point where T is equal to 0. We are with a calculator for this, but I could test points that are before and after this to see what's happening to our slope. So I'm going to go ahead and plug in 5 ln 3 squared into our calculator. Not sure if that fired. There we go. Okay, so we've got 30.17. So I'm going to plug in a value before that and a value after that to see if our slope is changing from positive to negative or negative to positive. So this is a first derivative test. into P prime. Around that value. Okay, so one number before it, one number after it. Go ahead and plug this in here. 1 minus 3e to the power of negative 0.2 times the square root of x. Open, open, close, close. Looks good. Okay, and then into y1. We'll plug in any value that is before 5 ln 3 squared, which we had was 30. So I'll go ahead and plug in, let's do 10. And I get a negative answer. Again, this is P prime. And hopefully we'll plug in a number that's bigger than 30.2-ish, and I should get a positive answer. Let's do 35 maybe. Okay, I do get a positive answer. Okay, so our slope is changing from negative to positive. Over to Nani. The slope of our function is changing from negative to positive. Is this a relative maximum or a relative minimum, or neither?
Minimum.
This is a relative minimum because we're changing slope from negative to positive. Okay, over to Jade. Jade, can you tell me why we don't need to test the start point and endpoints for this problem then?
Because if it goes to infinity.
I think you've got the right idea. So right now we know that we don't change slope at any other points. So if I have to go down from the start point to get to 5 ln 3 squared, and then go up from 5 ln 3 squared to get to the end point, then my lowest point has to be the relative minimum. Okay, so I can say something like this. Zoom out so you guys can see what we're writing about too. P prime t is negative on 0 to 5 ln 3 squared. Positive on 5 ln 3 squared to infinity. Therefore, P is at a minimum when T is 5 ln 3 squared. Going back up, our T right now is measured in days, I believe. Yes, days. So we are at a minimum value in the middle of day 30. So that means our amount of pollutant in the lake is decreasing until sometime in the middle of day 30. But then the pollutants actually start increasing again. Okay. For part C, I want to know whether the lake will be safe when the number of gallons of pollutants is at a minimum. Going over to in B, our lake will be safe if it contains 40 gallons or less of pollutant. What do I have to do in order to figure out whether our lake is safe when the pollutant is at a minimum? Give me a second, she's typing only. Okay, MP again, question is, how do we know what the number of gallons, whether the lake will be safe or not when the gallons is at a minimum? We said P is at a minimum when T is 5ln3 squared. Okay, not sure. In order to be safe, the lake needs to have less than 40 gallons of pollutant, or 40 gallons exactly. Nani, do you have any clue?
Could you ask again?
Yep, so we're on part C. I want to know whether the lake is safe when the number of gallons of pollutant is at a minimum. For part B, we found out that the gallons of pollutant is at a minimum when T is 5ln3 squared. And we're told that the lake is considered safe if it has 40 gallons or less of pollutant. So how do we know if the lake is safe when the pollutant is at a minimum?
Then we plug the 40 gallons.
Okay, we're pretty close. So I'm going to plug in the T value that we just got into our P. And if it ends up being 40 or less, then we can say that the lake is safe.
Oh.
Okay, so in order to do that, I do need to get an equation for P. And that means we will need to integrate our P prime T in order to get our equation for P. Going over to Jade. Jade, I want to set up an equation for P of T. What should our equation be?
Integrate of P prime T.
Okay, I'm going to integrate P prime T. From what point to what point? So from what time to what time?
Integrate 0 to 5 ln 3 square.
Okay, you're right. I'm going to write T in general so that I can keep using this formula, but I'm going to integrate from 0 to T of P prime T. That tells us how much, if I integrate this will be P of T minus P of 0, right? So that tells us how much additional gallons of pollutant are in the lake. However, what else do I need to add to this in order to figure out how much pollutant is in the lake total? I can see your microphone's on, but I can't hear. Can you say again? Still can't hear.
Can you hear me now?
Oh, yep, I can hear now. Okay, so what should we add?
50.
Perfect. We need to add how many gallons of pollutant were already in the lake at time 0, or P at 0. Okay, we can check and make sure our equation balances, but here's my general form of what just happened. So when I integrate this, I'll get my new function P of t, and I'll plug in our upper bound to subtract our lower bound. So this will become P of t minus P of 0. If I add P of 0, then the negative P at 0 and the plus P at 0 will cancel. And I'll be left with P of t equals P of t. So our equation balances as long as we add our start point there. Okay, so now I'm just going to substitute into this line here. I need to integrate P prime t from 0 to t and then add P at 0. We know P at 0 already was given as 50 gallons. This part though, here in green, I'm going to have to get by plugging this into our graphing calculator. So I'll go ahead and do that. This is, right now I've got, P prime as y1. So what I'm going to do is I'm going to integrate y1. So that's math integrate. Variables, y variables, function, y1. I'm integrating y1 in terms of x from our start point at 0 to our end point at 5 ln 3 squared. Open, 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 close, oops, close, close. Okay. Okay, just wait a second and let that run. And there we go. So we've got our integral. So my integral is negative 14.9-ish, 14.895. At the time, five ln 3 squared. Okay, so if I add that to our 50, we get the total amount of pollutants that is in the lake of 35.1-ish gallons. Going back to NB. NB, based on our requirements for pollutants, is the lake safe at this time? Yes. So the lake is safe because we have 40 gallons or less of pollutant total, which was within our threshold. So I've got set this at the right time too. P at 5 ln 3 squared is roughly 35.1. As P at 5 ln 3 squared is less than 40, the lake is safe. at that time. Okay. Any questions on A through C so far? I think when I go to D, I'll have to cut off all the rest of this. Okay, so for the last part of this, the investigator is using a tangent line approximation to P at T equals 0 to model the amount of pollutant in the lake. I want to know at what time does the model predict that the lake becomes safe? So first, the tangent line approximation. A tangent line approximation says we're going to use a line with the slope of P prime T at the time T equals 0 to estimate whether or not we will have a set amount of pollution so far away from T. Okay, so what that looks like is this. A tangent line is the line that touches our actual function at one point. Because we know what P prime is, we can get our slope of the line. Okay, so this is our point slope form. As long as I know one point and one slope, we'll have a line. Then I can plug in any x value we want, and we'll be able to get our y value. For us, our input is t and our output is p. So I could rewrite this point slope form like this. Something like this. So I can plug in any time t that you want into this equation, and we'll be able to figure out an estimate for what our pollutant will be at that time. So this is a tangent line approximation. We're using a straight line with one point and one slope that we know. We know at the time 0, there was 50 gallons of pollutant. So I can substitute 50 for P at 0. By plugging in T equals 0 into P prime, which we know the equation for the slope of, we'll be able to get an M value, P prime at 0, that we can substitute. And we'll be able to solve for P at T. Okay, I'm going to move this down to our box. We'll keep going from there. Zoom out actually. Okay, I'm going to copy our function really quick. Change colors. We were told P prime at T was equal to 1 minus 3 e to the negative 0.2 root T. So therefore, P prime at 0 is equal to what? Let's see, I've done J and I've done NB, so we're over to Nani next. Nani, if I plug in 0 right now, what will happen?
It will become 0. It will become
Okay.
1 actually.
Okay, the powers will be 0, which means this whole term e raised to something is 1. So that leaves me with P prime 0 is 1 minus 3 times 1. So what is p prime at 0?
It's 2. -2, sorry.
That's okay, -2. And then we were given also the amount of gallons of pollutant in the tank at the start point, or p at 0 was 50 from the original problem. So using that, I'm going to plug all of that back in and finish this off. Let's just keep working down here. I've got our p at t is what we're trying to solve for. Minus 50 is equal to our p prime at 0, which we said was -2 times t minus 0 is t. Okay, and that gives us a general equation for making an estimate of the pollution in the lake using a tangent line with our starting slope and point. Any questions on what we've done so far? Okay, I'm going to go back and we'll see what they needed us to use this tangent line for, and we'll see what values we need to plug in. Okay, I want to know at what time does this new linear model predict that the lake will become safe? Over to Sai. So we have a new linear model here. We were told our lake becomes safe when the pollutant total in the lake becomes 40 gallons or less. How can I find out when P at T will be 40 or less using this equation? Okay, I'm gonna rewrite this really quick and solve for PT, just adding 50 to the other side. Okay, so if our estimate for PT is -2t plus 50 using our tangent line approximation, I want to know when will PT become less than 40 or equal to 40?
So PT. Like, is it in equation, like something greater than or something smaller than?
Yes, so what should our inequality be?
40 is 40.
Okay.
40.
Oh, there's all my
Yes.
instructions tried. Okay. Sorry, deal with the delay. 40.
40 less than -2t plus 50, less than or equal to.
Perfect. Okay, so this should tell us when our approximation is less than or equal to 40. Okay, so now I just need to solve for t. Sai, I'm gonna stick with you. What do I need to do next?
Subtract both sides by subtract 50 from both sides.
Perfect. So that leaves me with -10 is less than or equal to -2t.
2t. So divide both sides by -2.
Okay,
phi less than or equal to t.
Something weird happens when I divide by a number here for our inequality.
Phi is greater than or equals to -2. No, 2. T. Oh no, it's just t.
Just t. Okay, so if 5 is greater than or equal to t, so I'm dividing by that negative number, I'm going to flip our inequality. Okay, so as long as t is less than or equal to 5, then p of t will be greater than or equal to 40. Rewrite that as one extra line up here. Okay, what you did was you substituted for pt with the equation that we had for pt and gave us a way to solve for t when pt would be greater than or equal to 40. So to answer the question then, and go all the way back up, and we'll jump back to NB since you can type this one. At what time does the model predict that the lake will become safe for our linear approximation model? Hmm. 5 hours and more. Okay, really close. We're measured in days, but you're right. The lake is predicted to be safe after day 5. According to our tangent line approximation. Okay. I'm just going through and checking to make sure we actually answered all the questions and I've got all the math in. Okay, is the amount increasing or decreasing? Why or why not? Okay, we did give a justification. Part B, for what value will the pollutant be at the minimum, and justify our answer. T is 5ln3 squared. There's probably already many units there too. That was days. After we started the cleaning. Is the lake safe when the number of gallons pollutant is at the minimum? Yes. Okay, so we've answered all of the questions as well. Okay, I'm going to go ahead and flash a scoring guide and we'll check against our work. Okay, so scoring guide's on the right, our work together is on the left. First one point as our answer with reason. The amount is not increasing at this time because p prime at 9 is less than 0. P prime at 9 is less than 0, therefore we are decreasing. Okay, that means the same thing, so we're good. 1 point. Answer with reason. 1 point for setting p prime at t equal to 0 to find critical points. Okay, we did that right at the beginning. And 1 point for solving for t. T ended up being 5ln3 squared. Okay, we did that. And then 1 point for our justification. P prime changed from negative to positive at that point, therefore it's maximum. Okay, we did do that here, but we also defined that in our explanation here, so we're good. Part C, I've got 1 point for an integrand. We were integrating from 0 to our time of our equation p prime in terms of t, and then added 50. I've got a general form for that, and then we plugged in t. But I do have the integrand. I do have the limits because we went from 0 to t and we defined our t here. So that's okay. And our conclusion based on the reason, our p at that t is less than 40, therefore the lake is safe. Yeah, that's good. And the last part, 1 point for getting the slope of the tangent line as -2. Okay, we did do that here. And then 1 point for our answer. The lake will be safe when the amount decreases by 10, which will happen at 5 days after we started. Be safe after day 5. Okay, we got that. So this would be full credit for us. Any questions on anything from here? Try to get everything in one shot. Okay, I do want to point out just how these scoring guides are going to work throughout the year. If you're just writing your final answer, you're not necessarily getting full credit. In fact, if you had everything correct, but you didn't show your work, then you wouldn't get a point for the first one because you wouldn't have a reason. And if you just wrote that p prime is at 9 is less than 0, you wouldn't get a justification point for your part B. But if you solve for t, you would get 1 point out of those 3 if you didn't show your work. If you just said the lake is safe, you would get 1 point out of 3 here. And if you said that it would happen at t equals 5, you would get 1 point for your answer here. So at maximum, you would get 3 points out of the 9 offered if all you did was write final answers. So it's really important for this class to show your process. If you have a process that works and is different than what's on the scoring guide, that's okay. And they will have alternate solutions offered for their readers, and point distribution set up for alternate solutions as well. All right, so we've got time for one more. Okay, similar idea. I have a tank containing 125 gallons of heating oil at t equals 0. In the interval from 0 to 12 hours, heating oil is pumped into the tank at rate HT gallons per hour, and it is removed from the tank at rate RT gallons per hour. So I've got a rate in and a rate out. We also have a start point here at 125 gallons of heating oil at t equals 0. Okay, first question is asking how many gallons of heating oil were pumped into the tank from 0 to 12 hours. I forgot I've got NB on chat only, so let me give myself a little bit of space and we'll pull up their chat again. Indy, I'm going to start with you. What do you think we need to do in order to solve part A? How many gallons of heating oil are pumped into the tank from 0 to 12 hours? Solve for t. So t is going to give us the time. We already know we want it at time t equals 12. Right now I've got h of t is a rate of change in gallons per hour that we're pumping oil into the tank. I have R of T is the rate at which we're pumping oil out of the tank. The question's asking for the amount, not the rate, of gallons of heating oil that were pumped into the tank. So only looking at rate in and then changing that to an amount. How can I find the amount of gallons of heating oil based on the rate in H of T that is pumped into the tank? Do I need to derive or do I need to integrate? Okay, I need to integrate, and we've got a rate. In order to get to an amount, I would need to integrate. When we integrate, we multiply our units together. So if right now, our axis would look like this, H of T measured in gallons per hour at any time measured in hours. Then when we integrate, I don't actually know what this function looks like, but something like this. When we integrate, we'll get the area underneath the curve. What we're really doing there is I'm multiplying gallons per hour times hours, which would give me gallons. So the integral of H of T will give me the total amount of heating oil that's pumped into the tank. Invi, back to you. I want to integrate H of T from what time to what time? Zero to 12, perfect. Integral from 0 to 12 of H of T dt. Okay, so I'm going to integrate. This is question 2, so this is with the calculator. So I'm going to go ahead and type our H of T into the calculator. Let's copy for that one. Let's clear all this out from last time. H of T is 2 plus 10 over 1 plus ln T plus 1. I'm going to go ahead and type in our RT2 in case we need it for later. So right now, Y1 is the rate at which gallons are being pumped into the tank of heating oil. This RT is the rate at which we are pumping out of the tank, is 12 sine of T squared over 47 gallons per hour. Okay, for the entire AP exam, everything is in radians. So I'm going to double check after typing this. Right now, if I hit mode, we are in radians. Okay, so I want to integrate from 0 to 12 of H of T, which in my calculator is Y1. Math 9 is our integration. I'm going to integrate variables, y variables function y1 in terms of our variable x from 0 to 12. That should give us our total amount. Okay, so the amount of gallons that we pumped in the first 12 hours is 70.6-ish. I'm going to write 70.57 gallons. Okay, so there are 70.57 gallons of heating oil pumped into the tank. For part B, I want to know whether the level of heating oil is rising or falling total at the time 6 hours. We are over to Jade next. Jade, what do I need to do?
Plug in 6 in the function.
Okay, I got cut off for just the first half there. Can you say that one more time?
Plug in 6 in each function.
Plug in 6 into each function. Okay, so you mean plug in 6 into h of t into r of t? Okay. So you're right, but I need to do a little bit more than that. When I plug in 6 into h of t and r of t, that's going to tell me the rate at which I'm pumping oil into the tank for h of 6 and the rate at which I'm pumping oil out of the tank for r of t, r at 6, at the 6 hour mark. How will I know whether the level of heating oil is rising or falling?
Minus falling rate in rising rate.
Yes, I need to subtract. Okay. So I could say there is some equation for an amount that we have not come up with. But when we derive that amount, the change in the amount, a prime at t, would be how much is being pumped in minus how much is being pumped out. Or h of t minus r of t is the total change in the amount. Okay, then I can go and plug in 6 and we'll figure out whether our amount is increasing or decreasing based on whether the change is positive or negative. Okay, so from there, I'll go into our calculator and we'll plug that in. So I need h at 6, that's y1 at 6, minus r at 6, y2 at 6. Variables, y variables, function, y1 at 6, minus variables, y variables, function, y2 at 6. And I get a negative answer, negative 2.92 gallons per hour. Write out hours since I wrote out gallons. Okay, so is the level rising or falling, Jade?
Falling.
Okay, the level is falling since our amount is decreasing. Just make that a capital A prime. Just to match my work over here. Okay, any questions on A or B from anyone? All right. Part C, I'm looking for how many gallons of heating oil total were there in the tank at the time T equals 12 hours. Nani, I'm going to go over to you. There are 3 things that I need to know in order to create an equation for the gallons of heating oil in the tank. So 3 parts to this equation. The total amount of heating oil in the tank is equal to. Can you give me one of our 3 parts?
HT.
HT is the rate at which we're pumping oil into the tank. So it's not just HT, but we need to do something to HT. HT is measured in gallons per hour, so that's a rate. This amount needs to be measured in just gallons. So do I need to integrate HT or derive HT in order to get an amount?
Integrate.
Integrate, right? And this is gallons per hour. So if we integrate, we'll multiply by hours, and that will give us gallons. Okay, that's going to represent the number of gallons of heating oil total that we pumped into the tank from T equals 0 until T equals whatever time we want. Okay, so that's the first part. The amount of gallons of heating oil total that we have is the amount of gallons that we've pumped into the tank total, or the integral of H of T in terms of T from 0 until whatever time we want. What else affects how much gallons of heating oil are in the tank? Anyone? So far I've got the total amount of gallons of heating oil in the tank is the total amount of gallons that we pumped into the tank. Jade, I don't have audio again.
Subtract the pumping out rate.
Really close. I'm going to subtract not the pumping out rate, but how much total that we pumped out.
Yeah.
How can I write
So,
that?
Integral 0 to T of T.
Perfect. Okay, so that is our total amount is equal to the amount that we put into the tank minus the amount that we put out of the tank. I've got one more thing that I need to know how much is in the tank total at any time. Anyone? So far I've got, here's how much we added to the tank. Here's how much we took away from the tank. That's not enough information to know how much is in the tank right now, though. I need one more piece of information.
125.
Perfect. We need to know how much was in the tank to start with, which was given as 125 gallons. Okay, but I'll rewrite this in words really quick. Okay, any questions on what we did? Okay, let me pull up NB's chat again. And then the last thing I need to do in order to answer the question. I've got a formula for the total amount of gallons in the tank. I want to know how many gallons are at the time t equals 12. So the last thing I need to do is just plug in 12 into this equation and we'll get our answer. Okay, so substituting. I think I am going to go ahead and do this as a separate, it's two separate integrals. Because our bounds are the same and we're integrating in terms of the same variable, it would be okay to integrate from 0 to 12 of ht minus rt dt. And you'll still get the same answer, but I'm not going to shortcut here. This is the integral of variables, y variables function y1 from 0 to 12. Oops, in terms of x. Okay, the integral of y1 in terms of x from 0 to 12. That's our rate in h of t. Minus the integral of variables, y variables function y2 in terms of x from 0 to 12, plus our starting amount of gallons in the tank. Should give us the total amount of heating oil that is in the tank at the time 12 hours after we started of 122.026 gallons. All right, any questions on C? Okay, last part. I'm looking for at what time would the volume of heating oil in the tank be the lowest? And then show how we got that answer. So in order to minimize the amounts, what would I need to do? In B, going back to you. I want to know when the amount is at a minimum. How do I find out when A of t is as small as possible? Okay, we've got an equation for an amount right now. I want to be able to minimize that amount. So this will be the same process that we had in the previous question. Choose a number and substitute. That would be a lot of guessing and checking, so not yet. I'm going to go back to our previous problem.
Do you put 0 in it? Plug
I'm going to.
0.
Okay, plug in 0 for what? Or set something equal to 0. What should I set equal to 0? Anyone? So,
8 hasn't gone.
okay, I think you said it. So a prime t should be set equal to 0. A prime because whenever our slope is equal to 0, we can be at a relative minimum or a relative maximum. Okay, and that is the same process that we did in the previous problem. For what value will the number of gallons be at a minimum for part B? We need to set the derivative of the amount equal to 0 in order to figure out when we are at a minimum amount. And that's because our slope will be 0 if we change from decreasing to increasing. Okay, so that's what we're going to do here. I'm going to set a prime t equal to 0, and then we'll solve for t. Okay, from part B, a prime t was already given as h of t minus rt. So plugging that in, whenever h of t minus rt is equal to 0, we should be okay. So I'm going to go back into our calculator and we'll calculate that. I'm going to go ahead and create a third equation, y3. That will be h of t minus r of t. So this is variables, y variables function y1 minus variables, y variables function y2. And I'm going to turn off y2 and y1 so that I'm not graphing them by hitting their equal signs. Okay, so now I'm only graphing h of t minus rt. And whenever this y3 is equal to 0, h of t minus rt will be equal to 0. So this should give us the time when this is true, which will be our critical points. Okay, I need to see all values from 0 to 12. So I'm going to hit window and we're going to change some things. My minimum value, I'm going to give us just a little bit of space so that we can see the printout in the bottom. This will be really from 0 to 12, a little bit of space. That'll be from -1 to 13 maybe. And then I only need to see when we cross 0. So from -10 to 10 should still be okay. And that's it, graph. Okay, I need all values where we touch 0. Looks like there are 2 of them. So a prime is equal to 0 at these 2 points, which we'll go ahead and calculate. So second, calculate a 0. It's going to ask us for a left bound, a right bound, and a guess. So I'm going to move my cursor until I'm to the left of the point where we hit 0 and hit enter. It's my left bound, then right bound. I'm going to move to the right of where we hit 0 and hit enter. And our guess, and this should give us the 0. Okay, our first 0 is at 4.79. I'm going to go ahead and store that value. Second quit x store alpha a. Oops. Alpha a. Okay, now whenever I hit a, we'll get that value. So if I wanted to do maybe 2 times a, I can do that in our calculator if we need it for calculation. Okay, I'm also going to get the second value. Second, calculate a 0. I need this one this time. So left bound, anywhere that is to the left of that 0 is fine. I'm to the left of the 0 we want right now, so hit enter. Right bound, I need to go to the right of that 0. And hit enter again, and a guess. And that should give us the 0 here as 11.32-ish. Okay, so I can quit X store as alpha B for practice. So I've got two values where our change in the amount was equal to 0 at 4.7 and 11.3. Okay, looking at our graph of A prime T here. A prime changed from positive to negative at our first point. Psi, if A prime changed from positive to negative at about 4.79-ish, was that a relative maximum or a relative minimum?
To negative to positive.
We changed from a positive value of A prime to a
Oh.
negative value of A prime. So is that a maximum or a minimum of A?
So maximum.
That is a maximum, you're right. I'm going to take a picture of this so I can label it. We'll add that here. I'm not sure what happened to the background there, but maybe. All right, I'm just gonna have to draw that picture myself, I think, because that's gonna give us a problem with our images mixing. And we had something that looks like this. And the other one was at 11.3-ish. I think. Double check. Yeah, 11.3 and 4.79. Okay, so the slope changed from a positive slope, that's where A prime is a positive Y value, to a negative slope where A prime was a negative Y value, which tells us that the original function was increasing until 4.79, decreasing from 4.79 to 11.3, and then increasing afterwards. So I've got a relative maximum here, a relative minimum at 11.3. I'm going to draw what our function looks like. We have some function that is increasing until 4.79, decreasing until 11.3, and then increasing after that. Okay, I wanted to know at what time the volume of heating oil was the least. So right now, because all we know are slopes, I don't actually know where the start point was. This start point could be higher or lower than this minimum point. So I'm going to need to check this minimum amount against the starting amount in order to be sure what the absolute minimum amount of heating oil in the tank was. If this minimum point at T equals 11.3, the relative minimum, is smaller than the 125 gallons that we started with, then that's the absolute minimum. If it's larger than 125 gallons, then 125 gallons is the smallest amount total. Any questions on what we're doing so far? Okay, update our work on the other side. So this was true when T equals 4.79 or T equals 11.3. 1.8. Okay. And then we did a first derivative test looking at our graph. About the points 4.79 and 11.318. Show that we were positive, negative, positive, which meant our original function did something like this. Went up, then down, then up, down, up. Okay, last thing we need to test is whether A at 11.318 is more than or less than 125. If it's less than, that's our absolute minimum. So here we go. My total amount would be this equation here, but I'm going to plug in 11.8. So that's the integral of variables, y variables function y1 in terms of x from 0 to b. That's 11.3 without rounding. Okay, that's the amount in at that time, minus another integral for the amount out at that time. Variables, y variables, function y2 in terms of x from 0 to b, plus our starting amount of 125 gallons. Should give us the total amount of gallons in the tank at the time b. Of 120.74 gallons, which is less than 125. So that is our absolute minimum at that time. I'm going to write out what we just did. Was equal to the integral from 0 to 11.318. Okay, so the last thing we need is a justification. So I need to write what we just did in words. The amount of oil increased until T equals 4.79. Decreased from T equals 4.79 to T t equals 11.318. And increased after t equals 11.318 as the relative minimum at t equals 11.318 was less than the starting amount. The amount in the tank was minimized at that time. That's probably more wordy than we needed, but that should give us credit for sure. Any questions on what we did for this last one, proving the minimum amount in the tank?
No.
All right, I'm going to throw this one up with the scoring guides again, and that'll be it for today. Okay, that is this one. So first one, 1 point for our integral of ht from 0 to 12, which we have, and 1 point for our answer of 70.57 gallons. That all looks good. So that's 1 point for integral, 1 point for answer. Part B, 1 point for answer with reason. Negative 2.92. The level of heat is falling at the time t equals 6. Okay, we're good. Part C, 1 point for our limits from 0 to 12. 1 point for our integrand. We're integrating h of t minus r of t, and 1 point for our answer of 122. Okay, down here we've got the integral from 0 to 12 of ht minus rt. So that's our limits. Our answer, what was the other one? And our integrand, h of t minus rt. That's good. Okay, for part D, set ht minus rt equal to 0 for the first point. Okay, we did that here. The volume is least at 11.318. Okay, the volume is minimized to 11.318. And the analysis for the absolute minimum means we checked against the start point as well. And we did do that. We checked against the starting amount of 125. So 9.79 total, and we should get full credit for that as well. Okay, so that's everything from today's homework.
Thank you.
Thank you.
Problem. I should have next set of homework up at some point. I believe this one's due tomorrow, so this will be either tomorrow or Monday. It'll unlock for everybody. Thank you guys so much for coming.
Thank you very much.
Bye.
Goodbye.
Thank